This video file is recorded in Sabancı University during the recitations for the CS201 Introduction to Computing course, as it was given in the fall 2016 semester.
Okay, just before going with the sorting algorithms, I just want to run the code again, and let me remind you that with the sequential sort we have a linear time, meaning that proportional to the input. If we had n words, we were going to check them one by one. With the binary search, we have logarithmic time, logarithm of n. That's why binary search was faster. Do we have to run the code again to demonstrate it to you? That no, we already saw it. That also practically we demonstrated that when the data becomes longer, then we can see it, we can sense it, that the sequential sequential search takes much more than the binary search. You remember that we did it with the longer data.txt part. Now let's go with some sorting algorithms, and after that I'm going to explain to you your homework, so please remind me about that. We already saw two of them, two of sorting algorithms, namely it was simple sort, called also select sort. We saw the insert sort. We will see two more sorts, bubble and modified bubble sort. Unfortunately, since you are afraid from the camera, I have to write numbers here and not sort you by your height, but it would have been much funnier, much interesting for you, and you could understand algorithms better if I sorted you with your height using those algorithms. Now I have to write numbers one by one, okay? But okay. Never mind. Probably you're not going to be famous. Now we have sorted the sequence 3, 7, 2, 1, 8, 9. And we are going to sort it with different algorithms. Let's start with the select sort. We already saw it, but let me write it again. So how it works, it's like this. We define an I, which goes, so we have the indexes here. This is, let me write it, okay, here, index 0, 1, 2, 3, 4, 5, okay. I goes from 0 to size minus 1, and size in our case is 5. Basically, in our case, it goes from 0 to 4. And here we have the I. J goes from I to size. And in each iteration, we find the minimum of the sublist that is left. Initially, we assume the minimum to be j initially, but this is initially. Of course, it might change during the course of the algorithm. So, we start with this one first. I is 0, okay? And j, for each I, j goes from I to the end, okay? So let me write it with red. This is for j. J goes here, then here, then here, checks all of them. But for one I, okay? So j will be in red. So initially j is 0, and I assume j to be the minimum. Of course, I'm going to compare them during the scope of the algorithm. So this is I here. Now let's see, which is the minimum index that should be put in the beginning. So 3 and so initially I said that the minimum is index, I put the index here, is index 0 is the minimum, but it might change. Now j is 0. I increment it to be 1. 0 and 1, which is smaller? 0 is smaller, okay. Then I increment j to be 2. 0 and 2, which is smaller? Well, 2 is smaller, index 2. When I say 2, index 2. Since index 2 is 2, this is 3. So, for the time being, the minimum index is 2. Then I compare 0 and 3, 2 and 3, which is smaller, the minimum, which is index 2, and the next one, which is 3, which is smaller. 3 is smaller, since it's 1. That's why I put 3 here. Then I increment j to 4, and I compare 3 and 4. So for the time being, still 3 is smaller. 3 and 5, so j goes to 5. So 3 is still smaller. I'm finished with this one, and the first pass, meaning from I to 7, is finished. So in the end, when it's finished, I swap the places of this index with the minimum I found. Basically, I've swapped index 0 with index 3. I is 0, minimum index is 3. I swap them. That's why I call the function swap. And here I have 1, 7, 2, 3, 8, 9. This is pass 1. Now, you remember, I was going from 0 to size minus 1. Now, we are finished with index 0. We have 1 there, which is the smallest of the whole list. Now, we're doing the same thing, but with a smaller vector, with this one. So we start from 1, and you see j goes from 1 to size. So this goes also from 1. The minimum index, initially I assume to be 1. So this is index 1, index 2, index 3, index 4, index 5. And I compare 7 and 2. Which one is smaller? Well, 2 is smaller. That's why the minimum is 2. And size is 2. Now I increase size to be 3, j to be 3. We go. Which one is smaller? 2 or 3, where index 2 is smaller? Okay. I increase size to be 4. 2 or 4, where index 2 is smaller. That's why you don't change it. I increase it to be 5. 2 or 5, well, 2 is still smaller. That's why I don't change it. I'm finished. Now I swap index 1 with index 2. Okay? So this guy, index 1 and index 2 are going to be swapped. And I have 1, let's swap, 2, 7, 3, 8, 9. This is pass 2. Now I is incremented to 2. Basically, I start with index 2, 3, 4, 5. I am done with those 2. Okay? This goes on like this. Up until I sort all of them. Basically, I should have in the end 1, 2, 3, 7, 8, 9. This is pass 5. Okay? Is this clear? This is the select sort that we already saw it. Okay? Why do we go from 0 to size minus 1? Let's say pass 4 will be 1, 2, 7. Let's say it's it's still going to be sorted, but we go up until here because this j goes to the end. So in the end, if we have only 2 more elements unsorted, it will be sorted with the last pass. We cannot go. We don't have to go to the end because j will go to the end. It will start at the place where I left, and it will go to the end. Okay. So this is pass 5. This is select sort. Insert sort. We already saw it, but here somewhere, let me show you how it works when we have an already. So this is not one number. Those are 4 distinct numbers, different numbers. That's why I'm going to do it like this. I just want to tell you if we have, and those are already sorted. How we do when we have to insert. What we do when we have to insert a number into an already sorted list. So let's say here we want to insert what? 4. And here we have 4 elements. With this 4 that we want to insert here, we will have 5 elements. That's why what we do is the following. I'm going to start from here. Basically, I have again 1, 3, 7, 8, and one more place. We allocate one more memory. Now we ask whether 4 is smaller than 8. If it is the case, this 8 comes here. Okay? Again, whether 4 is smaller than 7. If it is the case, yes, it's the case, we shift the 7 for one more place to the right. So it comes here. Now we check whether 4 is smaller than 3. No, it's not. That's why we put 4 to be here. Basically, with insert sort, we shift elements up until they are smaller. We shift the elements if they are greater than the element we want to insert. Of course, if they are greater, we shift them, and we stop at the time when the element is smaller than the element that is going to be inserted, or if we come to the end. Okay, we cannot go more than 1. Okay, to index -1 and so on. Okay, so this is just to show you how we can insert an element in an already sorted vector. So how will insert sort work with this vector here? 3, 7, 2, 1, 8, 9. And this shifting part here, shifting 7 here, shifting 8 from one place, 7, and so on, this takes a lot of time, kind of, okay? Because if the vector is large, and just imagine we have to insert it in the beginning, we have to make a lot of shifts, okay? So it takes a lot of time. But well, what if we want to insert 9? How many shifts do we have to do? Here. How much? None. But if you want to insert 1, 0, let's say, we have to shift all of them. So remember this. If we want to insert something to an already sorted vector, which is in the end, then we don't have to make any shift. It's much faster. Otherwise, if we want to insert something in the beginning, we have to make a lot of comparisons. Since we compare 4 and 8, it takes time. We shift 8, it also takes time. Okay? Remember that, because we're going to need it. So insert sort, it works like this. We have 3, and we want to insert this to the already sorted vector, so we have 3, 7. Okay? Those are already shifted. 2, 1, 8, 9. This is pass 1. Then we want to insert this 2 here, to those 2 elements, so we will have 2, 3, 7. And how will be inserted? In this manner, by shifting 3 and 7. And we have 1, 8, 9. This is pass 2. Then we want to insert 1 here. We should shift all of them. 1, 2, 3, 7. We have 8, 9. This is pass 3. We want to insert 8 in already inserted sorted vector. So we have 1, 2, 3, 7. We don't have it to make any shifts here. That's why we put 8 in the end. This is a good news, because we don't waste time by shifting. And in the end, we put 9 here. This is pass 4 and pass 8. 1, 2, 3, 7, 8, 9. We still don't have to make any shifts. This is pass 5. Okay. Now let's go with another type of... You see, those are different. Which one do you think is better? This one or this one? Faster. Insertion is faster because in this case we go from the beginning till the end. From the beginning till the end. We don't go like this. Okay, we put it. We just increment the number of sorted elements. We just insert. So this is faster. Definitely. Now let's see another sort, which is called bubble sort. Do you know what's a bubble? I think I have to... Okay, bubble sort, I will write it here. So bubble sort. Do you know what's bubble? Underwater, when you release some air, it comes up like a bubble. Okay, that's bubble. And we have a bubble sort. Why do we call it like this? I'll show it to you in a while. So we have again 3, 7. I want to sort the same list again. 3, 7, 2, 1, 8, 9. I'm just giving the algorithm now, and the code will be obvious. You can write it on your own. We start from the beginning, and this is what we do basically. Which one is greater, 3 or 7? 7 is greater. Then, okay, then we continue with 7. 7 or 2? 7 is greater. We switch places. So we go from start up until we come in the beginning. So we have 3, 2, 7, 1, 8, 9. Okay? But remember, we are left here, index 3. Now we go with index 4. Which one is greater, 7 or 1? 7 is greater. Switch places again. 3, 2, 1, 7, 8, 9. We left here, 7 or 9, it's okay, 7. 8 or 9, 8, it's okay. So here we end, and 3, 2, 1, 7, 8, 9 will be pass 1. Basically, it's like this. An element as a bubble, if it sees an element that is greater than it, then it continues. For instance, we start with 3 and 7, okay, 7 is greater. Then 7 and 2, okay, this should go here. They switch places, 7 is here. Now 7 and 1, 7 is greater. As a bubble, it goes in the end. They switch places. Now 7 and 8, 7 is smaller. 8 continues, 9 continues. So in each pass, a kind of those elements that are higher with value, with higher values, a kind of like a bubble go to the end, okay? That's why it's called bubble sort. So this is pass 1. We start from this index. Pass 2, we will start from this index here. With bubble sort, what in the end of each pass, we are sure that the last element is, here we make sure we select sort that the first element will be the smallest one. With bubble sort, the last element will be the greatest one, okay? So let's go with pass 2. Actually, here we start from the beginning, again and again. So, 3 and 2, which one is greater? We will have 2, 3, 1, 7, 8, 9. Okay? So we start from the beginning. And we repeat it n times. Then 3 and 1, they shift places. So we have 2 stays there, 2, 3, 1, 7, 8, 9. Okay? 2, 1, 3 actually. Now 3 and 7, it's okay. 7 and 8, it's okay. 8 and 9, it's okay. This is pass 2. 2, 1, 3, 7, 8, 9. Okay? Now again, we start from the beginning. 2 and 1. 2 is heavier, that's why they switch places with 1. We have 1, 2, 3, 7, 8, 9. 2 and 3, it's okay. 3 and 7, it's okay. 7 and 8, it's okay. 8 and 9, it's okay. We don't have to do anything. So basically, pass 3, 1, 2, 3, 7, 8, 9. This is pass 3. And we are finished here. Okay? But with bubble sort, so remember, we should have 5 passes. Because we have 6 elements, so at least we should pass it 5 times. Although it's obviously that it's sorted, bubble sort still continues. So we start it once from the beginning, twice, 3 times. Now for the 4th time again from here. 1 and 2 we don't have to make changes. 2 and 3 don't make changes. 3, 7, 7, 8, and so on. So we don't make changes, but still we have to pass it. So this is pass 4. And this is, again, pass 5. In this case, it was a kind of coincidence, since you see 8, 9 were already sorted, okay, in the end. But just imagine if we had 0 here and 4 here, we would have gone to at least 4 passes, if I'm not mistaken. You can check it at your home. So, and you have a clue what is bubble pass. We pass the vector from the beginning to the end n times, size times. And in each pass, a kind of heavier numbers float as a bubble to the end. Okay, again and again and again up until they are sorted. So this is the bubble sort. And in order not to repeat this, you see, in the pass 3 and pass 4 we don't have any changes. That's why we have something which is, we can put, in order to make the sorting algorithm be more faster, we can put something which is called flag. It can be 0 or 1. 0, let's say, it means if we don't make any changes in one pass, we don't have to go to other passes. Okay? Just imagine if we had something like this: 1, 3, 5, 7, 9, 10. Those are numbers which are already sorted. With bubble sort, we will have to go 1, 2, 3, 4, 5, 6 passes. Okay? Although they are already sorted. That's why we put a flag and we say, okay, we pass them. Did we make any change? No. If we don't make any change in any of the passes, we don't have to continue with other passes. Well, that's why we use a flag. If we make one change, as we did here with those small arrows, so we changed 2 and 3 here, again 3 and 1, 3 and 7, and so on. If we make any changes, then this flag is going to be 1, meaning that, okay, I made changes, it might not be sorted. So if we put this flag, then we are dealing with modified bubble sort. Meaning, if in a certain pass there are no changes, don't go to other passes. This is modified bubble. So we have been dealing up until now with 4 sorting algorithms. There are plenty more, and those are not even the best ones. There are some others which are harder to understand, but I'm telling you, you are going to deal with sorting problems and much more in the algorithms course, which is like 2 years from now. But sorting problem is an important problem. Now, which one is better, bubble sort or modified bubble? Modified bubble, because you don't go to passes, okay? But checking for the flag also takes time. So if we use all the passes, meaning that we use all the passes, the modified bubble will be a bit worse than the bubble because we are checking for the flag. And checking the flag takes time. Is the flag changed or not, blah, blah, blah. While for the bubble, we don't check the flag. But in general, modified is better because we don't have to go to another pass if we didn't have changes in one pass. Now, if you understood all those algorithms, you will not have problems with the following piece of code. Now let's go to the last example for today, which is called sort comparison. You can already open it as a solution. So I'm opening it. The code is here. We don't have to explain it in details. I just explained the algorithms. And in general, we saw that, okay, you said that insert is better than select. You're right. We also said that modified bubble in general is better than bubble. But we should also check in the cases when we have to sort an already sorted vector. What do you think? What's going to be the case? In bubble sort, it's trying to sort it, okay? But in modified sort, if we try to sort this one, 1, 2, 3, 7, 8, 9, which is already sorted, we will not make any changes, okay? However, if you try to sort something in reverse, let's say we have 9, 8, 7, 3, 2, 1, then modified bubble will be worse than bubble. Why? Because we will have to go through all of the passes. Okay, so bubble goes to all of the passes, and modified bubble also goes to the passes, plus it checks the flags. That's why it's going to be worse when it's sorted in reverse. Okay, we give the vector sorted in reverse, and we want to sort it in, let's say it's in descending order, we want to sort it in ascending order. It's in decreasing order, we want to sort it in increasing order. And the interesting part of the select algorithm is that the select algorithm doesn't care whether it's sorted or not, whether it's in reverse or not, whether it's a random list or not. It's approximately gives always the same results. Another thing, what do you think? Does it take more time to sort a list with 100 elements or with 1,000 elements? What do you think? Which takes more time? Of course, 1,000 takes more time, okay? That's why we are going to do some comparisons. And it's an interesting stuff, actually. Just let me arrange the font. So I'll start with array with 1 element. I'll go to array with 5,001 elements, and I want to increment it by 1,000. So this is the data that you get with insert sort, with select sort, with bubble, and modify. When we have random vector meaning that you have a vector which is not sorted. Not in ascending, not in descending. Random numbers, just like this one, 3, 7, 2, 1, 8, 9. This is the time. When the array has one element, okay, let's see. When the array has one element, insert takes 0, select 0, bubble 0, modify 0. It's obvious. When you have one element, it's already sorted. If you have 1,001 elements, the program is still running though. That's one. So, when we are dealing with random numbers, just let it finish, and we are going to discuss about this program. Things that I have already told to you. Okay, this is it. Now, when I ask you which one is better, insert or select, you said insert is better, and it's right, because select goes from the beginning to the end, again, n times, okay? Meaning n squared. You see the select here? I go from the beginning to the end, again, again, again. But here, I just insert it and increase the length of the sorted vector. Insert it, so insert is faster. You can see it here, when we have random vectors. Also modified bubble is faster than bubble, because we don't go to more passes, okay? We can see it here. But this is with random vectors, as it was the case with the illustration shown on board. But when the vector is ordered, you see insert is working pretty well also. Select doesn't make any change. It's approximately the same, you see? The values are approximately the same. The bubble, when we have we want to sort an already sorted vector, okay? The bubble, modified bubble doesn't do anything. Can you tell me why? Because of the fact we will do one pass, and we see, okay, we have 1,000 numbers, but it's already sorted. We don't have to go to the second pass. Well, so this is modified bubble. But bubble goes to all of passes, 1,000 passes, and it takes time. But it takes less time because we don't have to make swaps. You remember in this bubble here, we swap 7 and 2, 1 and 3. When it's already sorted, we don't make swaps. Okay, that's why it takes much less time. Let's say with 1,001 elements, we have this much seconds. But with 1,001, we have kind of double. Or with 5,001 elements in the list, we have this much seconds. And when the vector is already ordered, we have this much, okay? Now what if we send a vector as parameter which is in reverse? Okay, and we want to sort it. So we want a descending order, and we send the vector in ascending order. You see the select is always the same. Whether it's random, or ordered, or reverse, it's always the same. Insert, pretty much takes more time. Can you tell me why? It takes approximately, it takes 0 time here, and it takes twice more here in reverse order than in random. Because remember the insert, we were shifting them, the numbers, okay? And this shift takes some time, okay? If we don't do any shift, it will be 0. If we shift all of them, as it is the case in reverse order, it takes a lot of time. But if it's random, on average, half of them will be shifted, half of them not. That's why the round number is in half. So you see, when we have in reverse order, let's say with 5001 elements, is 2.42, but in random, it's 1.28. It's a kind of the middle. For 5001, you see 128. Here we have 242 in reverse and random. Then we have 157. There we have 0.79, which is the half because of the shifting part. But the interesting part here is, you see which one is better here, bubble or modified bubble? Again, modified bubble, although it might look strange, values are approximately the same. But you might think that, okay, you can assume it's the same because checking the flag doesn't take a lot of time. Because here, for sure, we will go with all of the passes. I mean, it's not the case when it was random. You see, here for sure you will go to all of the passes, so approximately the values are the same. Now, if you want to see the code, I'm going to show it very briefly. Again, which one we will use from all of those 4? Which is your preferred one? Which one? Insert sort. We'll go with that one. You remember the times also. Let me run it again. So 1, and let's say 500, and I'm going with 100. So you can check it from the times, you know. Maybe 100 is less, but you know, insert is much quicker than the others, on average. That's why insert is the better of those 4 algorithms. Now here, you have the implementation of bubble sort, modified bubble sort. So you take a vector, this is the size of the vector. You implement the logic that I explained on the table. For the select and insert sort, there are algorithms in this file here, in this comparer, yeah, here, no. I mean, insert, where was the algorithm? Yeah, sort all. So here you have the implementations of many algorithms here that you know, you don't know. So insert sort and select sort are also part of this list. But we saw the implementations like in 2 hours ago. So we're not going to see it again. Now this is you have the prepare vector function. You have 3 modes. One of the modes of working is when the vector is random, the vector is already sorted, and the vector is sorted in reverse order. So if the vector is in mode 1, it's a random vector, as you see on board. If mode is 2, the vector is ordered, and if mode is 3, the vector is sorted in reverse order, and you see it here. This is to prepare the vector. Okay, we send the mode. The count is the number, the size of the vector. We send the vector also as a parameter, the mode. If the mode is 1, then it's random. Okay. If the mode is 2, then it's in reverse order, meaning not equal to 3. So this is how we do it. Maybe we should write it. If mode is equal to 2, then it's already sorted. It works the same. So you see KK 0, 0, 1, 1, 2, 2. This is already sorted. Else, if mode is equal to 3, then it's sorted in reverse. You see K and count minus 1 minus K, meaning the size of that. So for index 0, we have size minus 1. For index 1, we have size minus 1, minus 1. For index 2, we have size minus 1, minus 2, and so on. Here we prepare the vector. And finally, here we do the part that we already saw here. I'm going to run it again. So let's say 1 and 5001 by 500. Okay. So this is the part when with those 4 loops, for each mode, 1, 2, or 3, random vector, 2 was, I think, sorted, 3 was unsorted, we print them. So random vector, ordered vector, reverse vector. We start with minimum size. Minimum size in our case was 1, up to the maximum size, which was 5001, and we increment it. Basically, the step is, the increment is the step that we increment the size of the vector in each iteration. So we start with 1, then we check it with 501, 1001 by 500. So again, you see we started here with 1, then 501 elements, 1001, and so on up until 5001. Since our input was 1, okay, our input here was 1, you can see it here, then 5001, and we incremented by 500 in each iteration as it's going here. Now you might ask how we calculate the time. There is something that you've not seen till now. We use timer. Timer is a variable. So we want to see how much time does insertion sort. We do the following: timer start, then timer stop. In between everything which is in between time start and timer stop is a kind of we have a stopwatch. We start counting the time to process this function. Okay. In order to use that, you have to define a variable of class C timer, of type C timer. So we do it here. And it has member functions start and stop, one of them. Here we start counting. It's like you press the stopwatch, you press it again, start it, and you stop it, okay? Elapsed time gives the difference, how many seconds have passed between stop and start. Actually, it gives it in milliseconds. You can make it in nanoseconds as well, okay? So, start, stop, elapsed time. This is for select sort. Then for bubble sort, you do the same. Start, stop, and elapsed time, and so on. For modified bubble, start, stop, you print it, okay? This is how we get this input here for all of the modes. This is for starting from 1 to 5001, incremented by 500. So you start from 1 up to 5001. Each incrementation iteration is by 500. And you do it for insert, select, bubble, and modified, okay? So from 1 to 5001, you increment it by 500. You do it for insert sort, select sort, bubble sort, modified sort. And of course, you do it for random vector, for ordered vector, and reverse vector. This is done in this part here. Another for loop. Mode is 1 to 3. If it's 1, it's random. If it's 2, it's ordered. If it's 3, it's reverse ordered vector. This is it. In order to use the C timer here, you have to include this library here, C timer .h. Did you see it in the lectures or not? Yes? No. Okay, well then you should see it. But three member functions are important. Start, to start counting, stop, to stop counting, and elapsed time gives the time elapsed between start and stop, between two presses of the button, if I can say so. Now, the homework. What should you do is something similar to your third homework, I think, and the sixth one. Very similar. So, this is your homework. You have a text again. This is your text. You have a pool. This is your pool. And you have an output. This is your output. For each input, which is consisted of the pool and the text, you have a corresponding output, meaning that you should do the following. You take a word from the text, let's say Boston, and you go to the pool and find whether Boston appears or not. If it does not appear anywhere, as you read it in that order, that will be the rank. So Boston is the first, Balkan is the second, Bunt is the third, because they are arranged so here, as you can see it. So Boston, no, which one? No, from the pool actually. No, I'm sorry, it's like this. You have a word first, and you have to find the correct appearances of that particular word. If it does not appear, you put it 0. For instance, can does not appear in the pool, so correct is 0. Or Boston does not appear, so correct is 0. But we have typos, meaning if only one mismatch occurs, it's one typo. One character is a mismatch, it's a typo. You consider a word to be a typo if the number of mismatches of the corresponding characters is smaller than the half of the length, as we already seen up until now. For instance, again, let's go to the text. We have Boston, and now we go to our dictionary, and we see that we don't find Boston here. That's why in the output, correct is 0, because we don't find correct appearances of Boston. But Boston and Phaeton have two. They differ in one character, namely Boston differs in the second character with Boston. It's one typo. Phaeton, no, which one? Another one was here. But actually, I mean, you have with one correct mismatch characters of length 1, you have 2. That's why typo is going to be 2. And you have the total here, which is the number of correct plus number of typos, and you put it 2. For Balkan, you don't have a correct appearance of Balkan, but you have Balkan, I think, which is one typo, and the total is 1, since 0 plus 1 is 1. The same is for the others. You rank them in accordance to the number of correct appearances of the number of total words, correct and typo, but it might happen as it's the case here. Boston and Balkan have 2 and 2 for the 2 and 1 for the total, okay? Or let's say which one? Balkan. Okay, so Boston has 2, Balkan is 1. That's why the rank of Boston is higher than that of Balkan. But Balkan and Bunt have both of them 1s for the total number of correct and typos. That's why what are you going to do is the following. You are going to sort them in alphabetic order. So if the number of total is the same, if total is the same, then you sort them in accordance to the alphabetic order. Again, B and B is the same, A and A is the same, but L, lexicographically ordered, is before N. That's why we put Balkan here, okay? And the rank of Balkan is 2. Is this clear or not? Okay, so correct words, you find exact matches. Typos, you find number of typos which are smaller than the half, but pay attention. If you have, let's say the length is 6, and you find mismatches with one word, with one character, okay, and then you find with 2 and 3, they are not counted. If you find with 1, you find all of them which are with 1, okay, just as it was the case in the last homework. The total is the number of correct plus the typos, and the rank is you sort them in accordance to the total. If the total is the same, then you sort them in accordance to the word, okay? You should use vectors to do this homework, 1. 2, when you are going to use vectors, you are going to use structures. You remember the structure, the struct ID student? Here you're going to do something similar. You might define a structure, and you'll have in that structure the rank, the word, the correct, the typo, and the total, 5 elements. For instance, you can do it with 3, the word, the correct, and the typo, since correct plus typo gives the total, okay? And if you have the total, then you can sort them. If the total is the same, you sort them by the name. You can make it with 3 fields of the structure, okay? You can make it with 5, with 4, with 3. But what should you do is the following, which is the most important thing. You should have a vector where you put those words, and those vectors should be as structures, and then you sort them. You can implement any of the sorting algorithms we saw today, or you can come up with your own algorithm. Any questions? Read for more details the guides. I mean, this is very briefly, just to tell you what should you do. Okay, if you have problems, you can email me. This is it. Thank you.